Good afternoon, class. Here's statistics practice test number 3, module 3, covering chapter 6 and 7. Chapter 6, normal probability distributions. Chapter 7, estimating parameters and determining sample sizes. And here's chapter 6, normal probability distributions. Again, I want to remind you of our pledge. I pledge on my honor that I will neither give nor receive unauthorized assistance, so on and so forth. However, you may use formula sheet, tables, and a graphing calculator. So we are dealing with chapter 6, normal probability distribution. The first question, answer the following. Part A, what percent of normally distributed data value lie within 2 standard deviations to either side of the mean? The answer is 95%. We want to discuss this further as to why and so on. Here's a normal distribution, which is bell-shaped, and the curve has this formula, y equals e to the power of minus parentheses x minus mu quantity squared over 2 sigma squared over sigma squared of 2 pi, or in this format, where e is the base of a natural log, 2.7182, and it continues definitely. Pi is 3.14159, and it continues indefinitely. Mu is the population mean, sigma is the population standard deviation. And so we are dealing with a normal distribution. So what do we know about the normal distribution? Short ND. The normal distribution ND or ND curve is bell-shaped. The mean, median, and mode are equal and located at the center. ND, normal distribution curve, is unimodal. That means it has only one mode. The curve is symmetrical about the mean. The curve is continuous. It continues indefinitely on the left and right. There are no gaps or holes. The curve never touches the x-axis. The total area under the curve, which represents the total probability, is 1 or 100%. The entire area under the curve is 1 or 100%. Therefore, each side covers 50% or 0.5 of the area. As you recall, the empirical rule, the area under the normal curve that lies within the this is called the empirical rule, 1 standard deviation of the mean, it's approximately 68%. So if we start from the mean and go 1 standard deviation on each side, if you start from the mean and you go 2 standard deviations of the mean is approximately 95%. That's why we are answering that. And if we start from the mean and we go 3 standard deviations away, we cover almost everything. 3 standard deviations of the mean is approximately 99.7%. Now, as far as how we arrive at that, you can go with the z-table. We're going to discuss the z-table in a moment. And the probability of z between these two numbers from -2 to 2, because 2 standard deviations away on each side, would be p of 2 minus p of -2. That means you calculate, it gives you the area all the way to here, and then you subtract this portion. That's p of 2, the entirely, and p of -2 is this one. And again, from the table, you get 0.9544 precisely, and it's 95.44%, or roughly 95%. So, in a normal distribution, values beyond 2 standard deviations from the mean, about 5% probability, are considered unusual. This 0.05 threshold helps identify statistically significant events in analysis, though stricter cutoff like 1% may be used based on context. In hypothesis testing, a p-value between 0.05 below 0.05 indicates that results are unlikely due to chance. According to the rare event rule, if a low probability event occurs, the initial assumption behind the probability will be flawed. That is why this 5% is important, and we'll discuss it further as we come across the concept of a test of hypothesis and the p-value. All right, so we're going to continue on that thoughts, and over here, answer the following. For a continuous random variable, the probability of a single value of x is always 0. Why is that? A single value does not cover any area under the curve. So we need an interval. The parameters of normal distributions are the mean and standard deviation. The mean for population is mu. The standard deviation for population is sigma. What are the values of the mean and the standard deviation for standard normal distribution? Short S and D, mu is 0, sigma equals 1. Standard normal distribution. So speaking of standard normal distribution, it gives rise to a table called the z-table or the z-score. Here's the negative z-scores, here's the positive z-scores. And the way you read the z-scores is the left column and the top row. For example, this one is negative 3.5. If you want to read this one, is negative 3.51. And this is for the positive. To the left of 0, negative z-scores. To the right are positive z-scores. And the concept of symmetry helps understanding. And there are certain values that are important. For example, inside we have the area under the curve. Okay. Inside is the area under the curve, whereas this is the z-score. All right, let's look at this case. We're going to find the value of z for a standard normal distribution such that the area in the left tail is 0.05. So first and foremost, you do the drawing. It doesn't have to be to scale, but drawing will help us see what's going on. So right here, the area is 0.05. And when we look at the z-table, okay, it looks like this. This is the area for the negative one. So we will look for 0.05 here, and I'm going to continue with more. This is for the limitation of the space that I have here. I don't give you the entire table. You have it in the previous page. And so we want 0.05. So over here, you look for 0.05. For example, this is the area 0.0003, 0.0006, and you look for it and you don't find it, but you notice 0.05 is between these two numbers. So negative 1.64, negative 1.65. So it's one of those or in between, and you choose it in between negative 1.64 and in between you're going to say negative 1.645 because of the way we read that. So that's how you read the table one more time. This represents the area. So inside we have the area. The left column gives you the z-score, and those are, what are the top row? The second decimal. So negative 1.64, negative 1.65, and we want it in between. So this top row is the second decimal. Having said that, if we were to use any type of technology, for example, TI calculator, we would go with second vars, standing for variables, inverse norm, and we put the entries. So we want the area to the left, which is 0.05, mu is 0, sigma is 1 for S and D, standard normal distribution, and we get this answer. And depends on where you want to stop as far as the number of decimals. As you can see, number 4, if you stop next to it is 8, you have to take it up to 5. So that's how you do the rounding, of course. And this is another um, calculator. There are many calculators we've already discussed, so I hope everybody's okay with that. If you use Excel, you put norm, inverse, and you put the 3 entries as well. All right, find the value of z for a standard normal distribution such that the area in the right tail is given, in this case, 0.1. You do a rough drawing, and the area in the right is 0.1. As you can see, this reads it for the left, and therefore we need this area for the sake of reading. So if the area to the right is 0.1, this area must be 1 minus that, because the total area under the curve must be 1. So having said that, we want to locate 0.9 here. So for example, this is 0.74, this is 0.82, this is 0.87. So you're getting closer in this area. This is 0.89, 0.89, this is 0.89. Okay, this is 0.9. Obviously, 0.9 is not there, but as you can clearly see, 0.9 is between these two numbers. So on the left side, you see the number 1.2 at top, 1.28 for 0.8997, or 1.29 for 0.9015. And so these are the two numbers in between. And z is between these two numbers. As I mentioned, 1.28 and 1.29. You can go with 1.285. Again, if you use the TI calculator, you put area on the left, which is 0.9 mu 0 sigma equals 1, and it gives you this answer, of course, with a lot more decimal. And if you want to stop here, 1 changes to 2. So 1.282. The reason it's different, obviously, because as I mentioned, we are dealing with technology that gives you a better idea. A more precise answer in essence. Find the following probability, probability of z larger than negative 0.82. Well, again, limitation of space, I'm going to have the table as such. The very first thing you want to do, you want to graph so you have an idea of what's going on. Now, because of the way the answers are, uh, it will give you the answer to the left. So probability of z larger than negative 0.882 is of interest to us. But what it will give us is the answer here, negative 0.82, negative 0.82. And remember, inside is the area. I made it larger so it becomes clear. That's the area, but that's the green area, the area to the left. So that's the green area. What do we want? We want the area to the right. So complementary event, 1 minus this number, and that gives us 0.7939 again. This area is given in the table 0.2061 because the total area under the curve is 1. 1 minus that is the answer. And we're done. Also, note over here, probability of z less than 0.82. In other words, if you go to z being a positive score, the area to the left of 0.82 and the area to the right of negative 0.82, these two are identical by symmetry. So it may be easier to read this from the positive z-values. This is by symmetry, identical. Again, you may use a graphing calculator and you put 4 entries, the left bound, right bound, and so on and so forth. And by the way, this goes from negative to positive infinity. Okay, so what do you put for the left side? Do you can put even negative 100 or negative 1000. For the right side, you can put 100 or positive 1000. Okay, okay. Now, lower is negative 0.82. Upper, I put 1000. Even if you put 100, is going to work. And why is that? As you recall, from the mean, 3 standard deviation to the left and right covers almost everything, 99.7%. So if I go beyond 3 standard deviations, so if I start from negative infinity and I go beyond standard deviation, almost covers everything, or if I go the other way around. So having said that, for the upper, you don't have to go too far. Even number 100 will do the job. And as you can see here, these two numbers, and 0.7938. Next to 8 is 9. We change it to 9. We go take it one notch up. The z-value for mu for any normal distribution curve is always 0. Why is that? Formula z equals x minus mu over sigma. And what you're doing, you're replacing the x with mu. The answer becomes 0. It's very straightforward. I hope everybody is following that. Everybody is okay with that. Usually, the normal distribution is used as an approximation to binomial distribution when NP and NQ are large. How large? Larger than or equal to 5. In some texts, and including MOM, my open math, larger than or equal to 10. The idea is that binomial distribution is discrete and normal distribution is continuous. So that's why, to make sure it works out, there is a restriction. The restriction is the product of N and P, as well as N and Q must be large. Find the area of the shaded region. The graph depicts the standard normal distribution of bone density scores with mean 0 and standard deviation of 1. So we want the probability of z larger than negative 0.93, where we are dealing with SND, standard normal distribution. So mu 0, sigma is 1. That's the first thing. Remember, it's an application. You want to read and write the given symbolically. Probability of z larger than negative 0.93. By now, we should know how to read the table. And we can go with the table or technology. Normal CDF from negative 0.93 to infinity. And remember, you would put some number like 100 to 1000 for the right. This is the answer. And again, 0.8238. If I stop here, next to it is 1. Therefore, it remains unchanged. So shaded regions, here's the second region. The graph depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. And we want the area between the two. First and foremost, let's write the given. Mu is 100, sigma is 15. Always write the given. We want the probability where x is between these two numbers. That is a normal distribution, everybody. We want to go to SND, standard normal distribution. That means we need the z-score. The formula is z is x minus mu over sigma. Mu is 100, sigma is 15. So we're going to put 106 instead of x. And the second one, 132, to do our calculations. So 106 corresponds to a z-score of 0.4. 132 corresponds to the z-score of 2.133. Now you can use the table or technology. And if you use the table, all the way to 2.133 is this number, all the way to 0.4 is this number, and you have to subtract this from there. Okay, so all the way to here and then to here. Of course, 106 corresponds to 0.4. Okay, let me just write that. So this corresponds to 0.4, and this corresponds to 2.133. So the area all the way from negative infinity to 2.133 is this number, minus the area all the way to here is this number. That's how you arrive at it. And you're done with that, or you can use technology. That's pretty straightforward. I hope everybody is okay with that. Assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Find the probability that a given score is between these two numbers, negative 2.13 and 3.77, and draw a sketch of the region. Always do that even if they don't ask you to do it. So what is given? Mu is 0, sigma is 1. Always start with the given. So we want the numbers between these two, negative 2.13 and 3.77. So in other words, probability of Z between these two numbers. And now you can use table or technology. So as far as technology, lower is negative 2.13, upper is 3.77, mu is 0, sigma is 1, and it will give you the answer. And however many decimals, for example, if I stop at the fourth decimal, since next to it is 3, it doesn't change, remains unchanged. 0.9833 is the final answer. Draw a graph and find P19. P19 means the 19th percentile. This is the bone density score separating the bottom 19% from the top 81%. So when you graph it, this area is 0.19. And this is the Z-score we are looking for. Okay. So graphing and then understanding the 19% and the Z-score. So if you use the table, you don't find 0.19, you find 0.1922 with this Z-score and 0.1894. By L, I mean the area to the left. This number gives us this Z-score, 0.1894 gives us this score. Notice 0.19 is between these two. 0.19 is between these two. So the answer is between the two numbers from the table. So negative 0.88 or negative 0.875. This is closer, that's why. I hope you recognize this is closer to 0.19 than this one. That's why. Anyways, if we go with the technology, inverse norm is used. Area is 0.19, mu 0, sigma equals 1, and minus 0.87789, and it continues. And obviously, the difference between this and what we got from the table is that this is much more precise as expected. So we are expecting it to be much more precise. So that's why, to a certain degree, it's a good idea to use the table. It's truly helpful, as well as the technology. All right. 3 out of 8 drinkers acquire the habit by age 20. If 300 drinkers are randomly selected using normal approximation to the binomial distribution, find the probability that exactly 100 acquire the habit by age 20. Okay. As always, application, write the given. We are dealing with BD, short for binomial distribution. How do we know that? Because there are basically two outcomes. N is 300. the probability of drinkers getting used to it. It's 3 out of 8, and we write that. It's important to know n is 300, p is 3 over 8 or 0.375. This is a binomial distribution, and so we'll take it from there. All right, let's remind everybody of what we know about binomial distribution. Probability of n factorial over x factorial times n minus x factorial, p to the power of x, q to the power of n minus x, mu is np, sigma is square root of npq, and q is 1 minus q. Therefore, q is 1 minus this number, which is 0.625. Now, remember, we're going to use normal approximation. A binomial distribution is a discrete random variable and a discrete probability distribution. So we want to make sure NP and NQ are large. So we're going to multiply 300 by this number and 300 by this number, making sure they are large, and clearly they are well larger than 10, and therefore we can use the normal distribution. So probability of x equals 100 is binomial distribution, everybody. Okay. And now to go from binomial distribution, which is discrete, to normal distribution, which is continuous, we use what's called a continually correction factor of 0.5. I'm going to explain that further in the next page because of the, limitation to the space. I'm going to do it in the next one. So we are going to add and subtract 0.5. And the reason is because probability of 1 point for any continuous random variable ends up being 0, because 1 point does not cover any area. You have to make up an interval. So statisticians have decided to go with only 0.5, although smaller than that, for example, 0.3 will do the job. So we go 0.5 to the left and right. That's an approximation. So having said that, we want to go to from a normal distribution to the z distribution, and z is x minus mu over sigma. Therefore, we need to calculate the mu, which is np, and sigma, which is square root of npq. So np, we've already done that, 112.5. Okay, and we're going to multiply it by q and then take a root. And sigma is 8.3853. Bear in mind, when you use technology, you use more decimal. So having said that, now we are going to use this formula. We have the mu and sigma we just found, and x, we put 99.5. We find the z-score for x of 99.5. Then we put 100.5. So for 99.5, we get negative 1.5503. And for 100.5, we get the z-score of negative 1.4311. So negative 1 is here, negative 2 here, both are in between. So we want this area. So we want the z between these two numbers, and always graph it between negative 1.55 and negative 1.43, between these two numbers. And so less than negative 1.43, you look it up from the table. Less than negative 1.55, you do the same thing. You subtract them from each other, you get this. If we were to use technology, normal CDF, the lower is this number now, and the upper is this number. So we are using with much more decimals, and we get the answer. If you go with binomial PDF and use 300, remember there was a limitation in the past that they didn't have access to a calculator. That's why we do that. And for that is not that big of a deal, but for other parts, it becomes a very hectic process to use the binomial distribution. And look at the answers. I hope you see all of them. If we stop here, next to 87 goes up to 8.0158. So the table is good within a few decimals. So we want to continue for part B, at least 125. The same question, at least 125 required to have it by age 20, and here's the given. Now I want to go over this concept that was mentioned. First of all, binomial distribution means probability of x larger than or equal to 125, which means we want probability of x equals 125 plus 126 all the way to n, which is 300. That's the meaning of it. And this is actually the reason we use the normal approximation, because it becomes very difficult to do so. So having said that, the normal distribution becomes what? Now, let me explain about this continuity correction factor. Use a continuity correction factor or continuity correction factor of 0.5. The continuity correction factor is applied when a continuous probability distribution is used for approximating a discrete probability distribution. Acts like a bridge between the continuous normal distribution and the discrete binomial distribution. So having said that, we have two choices. We can say, okay, if we want to go to normal distribution, we are going to say probability of x larger than or equal to 124.5 or x larger than or equal to 125.5, because I don't want you to memorize just, okay, in this case we do this, in that case we do that. No, just put the number, the very first number here, discretely would be probability of 125, and it continues, right? Whereas this one, the first one would be probability of what x equals 126, and it continues, right? If you look here, we need this one, and if we use x is larger than 125.5, this won't work because we're gonna miss that. So we're gonna go with 124.5. So that's binomial distribution. This is normal distribution, and we're going to use the z-score of x minus mu over sigma. We already have mu and sigma. X is 124.5, and you do the math. This is the z-score probability of, again, I'm going to repeat, this is extremely important to understand. Binomial distribution probability of x larger than or equal to 125. Normal distribution probability of x larger than 124.5. By the way, if you have an equality or not makes no difference for the continuous distribution. Probability of z larger than 1.4311, and it's important, let me erase my word. It's important to locate that this is the area we want. Always graph so you don't make a mistake. Clearly, this is not a huge area. This is larger, so you have an idea what to expect. 1 minus that. Why 1 minus that? Because this area from the table is 0.9236, and the rest of it is what you see. It's very straightforward, everybody. Now we're going to continue with the same question. That's why we are repeating the given at most 165. So probability of x less than or equal to 165, which means discretely, probability of x equals 165 plus 164 and all the way to 0. So this is the key, the endpoint, because there are two ways to write this. Let me write that. Probability of x less than, doesn't matter if you put equal or not for normal distribution, 165.5, or probability of x less than 164.5. Remember, we either have to subtract or add 0.5. In the case of 1 point, you add and subtract. When you have less than or equal, you have it. So take a look at the very first discrete value. The first discrete value here, less than that, it's probability of x equals 165, and it gives you the rest of it if we were to go with binomial distribution. Whereas here, the first one, The first number less than this, but a whole number, a discrete number is 164. And so what happens? We miss this one. Therefore, this is out. So probability of X less than 165.5. Let me erase my work. And again, the z-score is X minus mu over sigma. Mu and sigma are given. You are going to replace the X with 165.5. And now probability of Z less than 6.3206. If you draw 6.32 is somewhere here, and area to the left of it is almost 100%. So in the table, above 3.5 in the Z table, they give you 0 point, and then 49, 0.9999. But for all practical purposes, it's 1 or 100%.